Okay, so this is the fourth week of this semester. So we will look into the modeling one, still modeling one, but last lecture we look into Boolean model and also the weight model, which is the term frequency. So today we will look into TF-IDF weighting model and also the um, vector model. So this is basically a continuous slide from the previous one. So today we will cover two parts. The first part is called TF-IDF. So we will look into term frequency, inverse document frequency, and what is the combination of this TF-IDF? How do we normalize the document? And the second part, we will look into the vector model. So based on the idea from TF-IDF, we will continue with the vector model. How do we apply vector model to perform the, how do we quantify the similarity between two documents or between the query and also the document. Okay. So what is TF-IDF? So TF-IDF stands for term frequency inverse document frequency, consisting of two formulas here, term frequency and also inverse document frequency. Both are used to evaluate how important a word with respect to a document. So at the same time also, the term may exist in the query. Okay. So how this TF-IDF is used? They are used to highlight terms that are significant. Those terms that occur very rare can be used to differentiate document, but those terms which are often occur in the document, for example, the, is, and then and, this occur almost in every sentence or every paragraph or every document. So this cannot be used to determine how important is this term with respect to the query. Okay, so we now want to have this stop word. This is called stop word. So the TF-IDF consists of two terms, two components, term frequency and inverse document frequency. For the Boolean model, if we recall back, the disadvantage of Boolean model is that we cannot perform the ranking, and we have to do exact matching. We cannot do partial matching, and at the same time also the result returned to us are too many or too few due to the fact that we have to do exact matching. Okay, and then we move on to frequent term. So frequent term highlight the importance of a term with respect to the document. So if a term occur many times, the term is considered important in that document. Okay, but we also have this another component which is inverse document frequency. Okay, so we will look into this. Why do we need this? Why do we need to multiply the term frequency with the inverse document frequency? Okay, so based on the learned assumption, they say that the weight of a key I in the document J, so this is your key, this is your document, is always proportional to the term frequency. So meaning that we are looking at the term frequency here. So we can use term frequency to be the weight of the key I in document J. Okay. So based on this observation, we're saying that the higher the frequency, the more important they are in describing the document. So we can say that, okay, since we have the term frequency weight here. So basically, we are looking at the how frequent that keyword I exists in J. So that is the term frequency. Okay? But we have another version, another variant of the term frequency in which we use log. Okay, the reason why they use log is to reduce the bias. I will explain later on, and also to reduce um, the value, the magnitude of your number here. Okay, so normally they use log base 2. Okay, and this one refer to the term frequency of keyword I in document J. So we only use this one when your frequency is above 0. So otherwise, your term frequency is 0. Okay. So like I mentioned just now, we use log to ensure that the importance of a term increases with frequency, but at a diminishing rate. So meaning that if your n is 100, so your value is only 6.64. So if your value is 10,000, so your value is, when you convert this one into log base to 10,000, the differences is too small. Not too small, but the differences are small. Okay, so we don't want to use peak value here to indicate the weight. So we use log 2 base 2 in order to reduce the um, value to a small number, so able for us to differentiate, still able for us to differentiate the weight of different term in different document. Okay, so that's the reason why we use log. So you need to remember this formula: 1 plus log base 2, and you want to find the term frequency for keyword I in document J. So that is the term frequency. Okay. So if this is 1, so log base to 1 is basically 0. So you still have 1 here. So remember that your frequency here must be above or greater than 0. So it could be 1 and 2 and 3. But if it's 0, so that means it will direct to here. Okay. So if you look at the formula that we learned just now, and how do we apply here? So what happened is, how do we apply this one? So this is, where's my mouse? Okay. So this is term frequency for I in document 1. So if you're looking at 2 here in document 1, how many? We have 1, 2, 3, 4, right? So we have 4. Okay. So the formula that we have is 1 plus log base 2. Okay. So this is the term frequency for keyword 2 in document 1. Okay, so when we compute this one, we will get 3. Okay, so that's how we get 3 here. So we look at the number of time that exists in the document. If we look at another example, for example, do in document is supposed to be 4, right? Or 3. 3 is this one. Okay, so how many times do exists? So do exists 3 times. Okay, so this one's supposed to be here. Just the circle, but the value is the same. Okay, so what we want to show here is that when we have the do here for document 3, so in document 3 we have 3 times, do exist. So we just plug in the value here, then we get 2.58. Okay. So let me move this one is here. Okay. So the rest of the value we can compute using the same manner. So that's how we construct the value here. But one thing that we notice here, if you look at here, all this value, they have values, right? So which means that this term is useless. Useless because we cannot use that term to be to differentiate the four documents here, because all of the document have this term B. Okay, so for that reason, that's why we need to have the second formula, which is the IDF. So now we know how to compute the term frequency, the first part of the formula. Okay, now we look at why do we need the IDF, inverse document frequency. Okay, so we want to refer to specificity, in which we want to know which term can be used to differentiate the document, and of course unique term is considered to be very effective in differentiating few documents. So for example, the term beverage is a general term. So of course, this one will occur more than tea or beer, because tea and beer, they are very specific, and hence they will appear less in the document. But if you look at the beverage, they refer to many specific items, so they may appear more many times in the document. Okay, so meaning that if you want to have a very specific term that can be used to differentiate the document, we need to have this T and B. So how do we find this word? So if you go back to this slide, so meaning that the term B is too general. We cannot use them to be one of the token that we can use to differentiate the document, right? Okay, if you look at here, the weightage for example, these two are only unique for document 3, so they are very useful. Okay, this term, although they have big weightage here, but they can they the weight cannot be used to differentiate document 1, 3, and 4. Okay, so a term that appear in many documents is less specific, so we don't want to have this one, so we want to remove them. Okay, so we want to keep only those terms that appear in few documents, because they can be used to differentiate document very effectively. So that's why we need this. It's called the inverse document frequency. Okay, so in the inverse document frequency, they are looking at the number of time that term exists in all of the document. So this is the total document that we have. Okay, so if your total document is n, and the term exists in all of the documents, so basically if you have this n and n, so the value will be 0. So which means that the term um, does not carry any meaning, or cannot be used to differentiate the document. Okay, so what we want to do is we want to have high IDF, but this is 0, so 0 means no meaning. Okay, so if we take this example, so if we say, okay, we have 1,000 document, and we look at this term, these three, and each of these term exists in 500, 150. So by looking at this number, we know that peer is very specific because they refer only 50 document only. So if we compute using the TF-IDF, your N here is 1000, and then your document frequency for term T would be 500, 150. So you will have this. So you look at this low, medium, high. So high specificity means they are very unique and very effective to be used to differentiate the document. Okay, so that's why if this beverage exists 1000 times, so that means your IDF will be 0. So 0 means they are meaningless. Okay, so why this IDF is important in information retrieval? Because it enhances the relevant ranking by reducing the weight of common terms. So all those terms that are too general, we have less weight. So all those terms that are very specific, very unique, they will have higher weight. Okay. So having said that, so now we have this IDF. So for example, like this, we have 4 documents, and then this one refer to how many document does the 2 term exist. So we have 1 and 2. Okay, so that's why we get 2. So you plug in the value, n is 4. So 4 divided by 2, you get 2 log base 2, 2 is 1. And then do we exist 1, 2, 3. So 3 document. Okay. So all this IDF will be kept, will be computed and kept. So in order to complete the computation of TF-IDF, we have to multiply them with the term frequency. Okay, so this is just to show you how to calculate the IDF. Okay, so the final formula is basically multiplying the term frequency with the IDF. So this is the first part. This is the second part. Okay, so the first part is to show which term are important in the document, and this term are used to highlight a very specific term and will ignore the less specific term that we have in the document. So this is like filtering. Okay, so please remember this formula. It will be confusing when you learn in the next chapter because we have set-based model, so which is more or less similar with this one, but this is your foundation. So this is only when we assume single term per row in your term document matrix. Okay. So for TF-IDF weighting scheme, we assume that individual item are independent to each other. Okay, so we don't capture 2 terms. We only capture 1 term at one time. Per row will give you the weight of that particular term and also the IDF for that particular term. Okay, so have to know this formula. Okay, so since we have the term frequency, the first part here, so we have the IDF, so we just multiply. So that's how we get the value here. Okay, so we know how to compute the IDF, we know how to compute the TF. So at the end, we just multiply 3 and 1, and then this is also 2.585 times 2, then you get 5.170. So these are the final term document, inverse document frequency that will be used for ranking. Okay, So in your project, you will do the same. So the first thing is what you need. The first phase is just to read this value. Okay, in the project, you will have 10 files. So you need to write a program that will read the 10 files and then tokenize the text document and then form this matrix. Okay, so you have plenty of time. Don't wait until last minute. If possible, you aim to finish the project by Christmas lah. Okay, so we are done with that. Okay, so in summary, so TF, this is a formula that we use to indicate the level of importance of the term within a document. So the higher the value, the more frequent they appear in the document. IDF is used to look into how specific is the term that we have in our uh, term document. So we refer to the number of document that consist that particular term. So if they exist in less number of document, they are more specific. Thus, they will have higher value. So the higher the value, it means that it appear in fewer document. So together, this we form the TF-IDF. Okay, so they balance the term frequency and term specificity. Okay, so this term document metrics are used in REG. REG is one of the terms that they use in LLM, large language model. So this one is retrieval augmented generator. Okay, so they will retrieve the document. So based on the ranking, they will summarize the content based on the similarity of the document. Remember that in LLM or ChatGPT, you have the prompt. So you ask anything. So what happens next is that based on the term that you type, they will use the reg in order to produce the output, and then they do summarize. Okay, so this concept is used in reg in LLM. Okay, okay. So but when we look at the document, some documents are too long, some documents are too short. Okay, in document that has too big size, when we make an assumption that a term exists many times, it's not fair for the document that has shorter version. So we need to normalize the document. Okay. So we do not want to have a bias ranking because term in long document may get inflated total weight simply due to the count word. Okay, so for example, for this one, this is 2 pages, this is 50 pages. Okay? But when we talk about AI, both AI, so we cannot compare directly the number of time they exist because this is only 2 pages, this is 50 pages. Okay, so before we can compare them directly, we need to normalize them. So we need to normalize the number of terms that exist in these 50 pages, and then we take that value and the number of AI divided by this value. Okay, so we will go through how to normalize the value here. Okay, so the problem that we want to solve is that longer document naturally have higher term frequency. So in order to have a fair or standard um, value, so we want to normalize them. So the solution is we want to um, divide them by the length of the document here. So this is your initial weights, and then this is the normalized weight. So we will divide this value by the length of the document. So how do we compute the length of the document? So basically we take the summation of all the square of the weight of the document of each component in the document, and then we take that number, and then we normalize the weight by dividing the weight with the magnitude of the document. Okay, so how this is done? Okay, so this is the initial weight. So we want to divide by the sum of all the square weighted component in that um, document, and take the square of the sum of all of this. Okay, so if you look at this graph, so each document will be represented as a vector, and the vector will consist of all the uh, weightage. So this weightage refer to word number 1, word number 2, up to word number T. Okay. So in order to find the length of the document, we just take the square of each of these weight and get the summation and take the square root. So this is the formula that we have. So this is similar to here. Okay. So that means for each weight that we have in the document, we will divide them by the number, by the length of the document. So how do we apply this? Okay. So for example, in document D1, we have 3 terms. We have 3 terms. Huh? Okay. So to find the length of this, we will take the square of each of them and take the square root, and we get 1. Okay. So the normalized weight for this one will be still the same because divide by 1. Okay. So that is okay. But for this one, for document 2, so we take the square of each of the component and then sum up all of them, take the square root, then we get 0.97. So meaning that for each of the weight in document 2, we will divide them by 0.97. So this is the normalized weight of the document 2. Okay, so that's how we normalize the value. Okay, so if you look at this, this is the TF-IDF, right? And this is the length of the document for D1, D2, D3, D4, and so on. Okay, so for document 1, so how do we compute the length of this document? So we just take all of this, take the square, and then take the square root, and you get this. So that's how we get this. Okay, so similar to this. Okay, so this is your TF-IDF, right? So if I say compute the normalized weight for this table, so what you need to do is you take this table, then for each of this value, you divide by 5.06. Okay, so you divide everything by this for here. And then document 2, you will get this, and so on. So once you have the um, normalization, so that is your table that is suitable or fair enough for all of them to be used for ranking. Okay, so that's the usage of document length normalization. Okay, any question? If you okay, can you type number 3? Okay, so in your project, the first project, let me show you that one first. So I will always remind you about the project so that you have time to think about your project and then um, start doing the project. Don't wait until last minute lah. Okay, can you see this? So this is question number 1. So question number 1 is very easy. So given the 10 files that you have, then you need to read those files. Okay, and that's a simple one lah, due in 10 of November. So the second part is to tokenize them, and then you need to construct the TF-IDF. So you need to apply the formula that we have learned today. So you need to find for each of the term that you have, you need to count how many times they exist in each of the document, and then you need to compute the IDF. Then you need to construct the TF-IDF, and then finally you need to normalize them. Okay, so that is um, question number 2. Okay, so this one later on. Okay, so you need to focus on these two first. So I think this one, if you really focus, you can finish in 5 days lah, 1 week lah. Okay. Those students who, based on experience, those people who manage to complete this one kan, for the project, they basically don't have to study for um, the final because they know the process. And of course, in solving the problem, you cannot simply ask ChatGPT to solve the problem for you. You need to be able to understand the coding and so on, how it works, how to modify the program, and then what is the logic and how they are computed. And then lastly, make sure that um, the output is matching with your manual calculation. Okay. So any question on the project? Yes, Daniel. Yes, that is only the first part lah. Very simple project just to get you all started. I don't want to burden you all with the worry that you cannot do the project. So just a simple one. Given the text file, read the file. You should be able to read and display the file. So next one will be, you need to think about how do how do you tokenize, extract every token, And then while you extracting, you need to count how many number time they exist, and then you construct the term document matrix and so on. Okay. So I know most of you will be using ChatGPT, but when the solution is there, then you need to understand the logic behind the coding and then the data structure that are being used so that easy for you to um, manipulate or customize the program. Um, it's all available in ITEL. So there are 10 files. So you can download the dataset and also the instruction. Okay, so what you need to hand in is just the coding and also link to the video explaining about your assignment. The coding language up to you. You can do use script or you can use Python or you can use R software as long as it produce the output and it should be okay. Okay, so um, for this project you will have 5 times to submit, right? So for the first assignment, there I put project 1 or project 1A. So you need to submit the project 1 before 10th. So I will issue the second one. So in the second one, so you will um, upload your solution for project number 2. Okay. Okay. So the project consists of 10% of your final marks. So very, very big chunk of your final grade. So please take advantage of this. Don't lose any of those points because these are the points that you can secure by spending more time on the project, learning more. Because when you do the project, you will keep thinking how it will looks like, how the processing looks like. Then you will tend to remember more about the formula, how it works. So for your midterm, it should be easy. Okay, so let's continue with the next one. So based on the previous semester, actually the previous lecture and this lecture, I combine one lecture. So it's very compact, so make student confused or not able to catch up. So now I split them into 2 sessions. I give you more examples so that easy for you to understand. I know Dr. James covered the same thing, but it's good to have 2 lectures. Then you have um, a lecture from different lecturers. It's like you learning a subject for 2 courses, but it makes your learning process more effectively. Okay, so we have covered this TF IDF, right? So now we cover this because we know how to construct the TF-IDF weight matrix, row, column, and then now we look into the vector because we will use this vector model to do the ranking. Okay. Okay. So if we recall back the Boolean retrieval model, document are retrieved based on exact matching only. We cannot do partial matching. Okay. So for exact matching, this is similar to structured data in which you perform the SQL statement, select this column from what table, and then what is the condition. So that is exact matching. So we want to have this vector model because vector model allows us to perform partial matching, or it depends on percentage. Okay? So for the Boolean, we either relevant or not relevant, 1 or 0. full matching or not matching. Okay, so these are the problem. We cannot do partial matching, partial relevance. Sometimes the result given to us too many or too few or none, because it's very specific exact matching, and we cannot perform the ranking because they based on 1 or 0 only. Okay, so for that reason they introduce what we call VSM, vector space model. So in a vector space model, they assume the query, the document are represented by a vector. So this vector contain the weight of each component of the query and document. Okay, so for example, like this is the weight of keyword I in the query. This is the weight of keyword I in document J. So this formula, we have seen this one. So we know this is TF IDF. So each component will have its own weight with respect to the query and the document itself. Okay, so each dimension corresponds to a term. So each dimension will correspond to individual term in your query and in your document. Okay, so each vector component, the term weight reflects the importance. So the bigger is the weight, the more important they are in the document. So this allow you to have partial matching because you are computing the interaction between the Q and the vector Q and document J, because we will be multiplying them in order to find the ranking. Okay, so the degree of similarity can still be measured, which is not similar to Boolean model. Boolean model, you just have 1 or 0, but this one you have decimal number. Okay, so to perform the similarity between the query and also the document, we can use the cosine function. So this is basically multiplying the vector of the Q and also the vector of the document, and divide by this. So this is similar to the normalization. So we take the length of the Q and also the length of the document. So we will have the similarity here. Okay. So since Q and document are vector, both must have the same length and they are corresponding to the same term. We do not want to have different length and different term corresponding to different term. Okay. So the result range from 0 to 1. Okay. So the dot product will capture the term overlapping, and the denominator are used to normalize the document and also the query. Okay. So to illustrate this, we have this. So the angle that we want to measure is this. So we use the cosine function. So if you have query which is similar to your document J, the degree here will be smaller. Okay, if they are similar, so that means the vector dj and vector q will be overlapping each other. Okay, so this is the formula. So if we look at how do we apply this formula, this is just to compare the differences between the Boolean and the vector space model. So for the Boolean, we have 1, 0, but for this one, we have weighted vector. Boolean model perform exact matching. Vector space model allow you to perform partial matching. This is all or nothing. This one is based on the similarity that we have. No ranking because you have all true For this one, you can perform the ranking because they will have different degree of similarity. Um, use case, so this is for keyword matching, and this one is used for search engine. Okay. Okay, so let's take a look at the example now. Okay, let's suppose we have this query, to be or not to be. Okay, so we want to compute the similarity based on document 2. So the first thing that we need to do is we want to extract the unique term that we have, which is to be or not. Okay, so to be or not. So we have to twice, and then B, and then B is twice also, and then or and not. So we have unique term here. So first thing that you need to do, you can either compute term frequency or you can compute the IDF. For the IDF, we look at the unique term that we captured just now. B, okay, this refer to the number of document that consists this term, and then we just compute them. So this is your IDF, this is your TF IDF. No, this is TF. Okay, so 2 exists 2 times, B exists 2 times, and then you compute using this formula, you get this. So that TF IDF will be this. So this is the vector for your queue. Okay, so based on the example for document 2, so document 2 you have this, right? Okay, but when we say, okay, for the query vector we have 1.3 and then 0 and then 2 and then 2. So this one is referred to 2B or not. Okay, so for that reason we will take only 2B or not in the document 2. So you have that value. Remember that the dimension for vector Q and vector document 2 must be the same. So you must take whichever matching and complete. You could also get all of this, but the Q must also have 0, 0, 0 if you decide to take this. Okay, so always remember you only count the one that matter here. Okay, so once you get the vector for Q and document 2, then you can perform the ranking. So basically what you need to do is just multiply the vector of Q and vector of D2, we get 0.6, and then we normalize them by computing the length of the Q and also length of document 2. Okay, so if you look at here, so this one refer to document 2, which is this. Okay, so we are not referring to this only. So remember that when you want to normalize, you want to get the full document content. So you need to take this part, okay, and not only this. This is simplified because you want to have similar dimension with the Q here. Okay, so for this you need to have, for the magnitude of document 2, you get to have all of them, then you have 4.8. So to compute them, you just plug in. Okay, so you get that is, I think that is 10. Let me check. Yeah, that is 10. missing here. Okay. So you double check the, so this is 2.6. Is that correct? This is 4, this is 4. Yeah, correct lah. So this one is 10.6. So we take the value here for the cosine similarity. So 10.6 divided by 15. So 15 coming from 3 times 4.8. So we get this. So that is the final value for the similarity between query and document 2. Okay, so the higher is the value, the more similar they are. Okay, let's take a look at another example, but with much simpler. So we now have a query called to do, and we want to compare with document 1. So we have the term to do here. So we have 1.0 and 0.415. Okay. So the query vector is 1 and also 0.415. So for document 1, although we have 3, we don't have to take all because so we only take to do here. But if you want to include the is here, for example, you want to include 4, and the rest here is 0. So it is same thing when you want to do the dot product. This one will disappear as well. Okay, to reduce the calculation, the error, we can just follow only this to do. Okay, so given these two vector, then we can just simply perform the dot product. Okay, and compute the magnitude, the length of the queue. Okay, so in this case, I show you this. We can have this or this, but this one we include another dimension, but it will give you the same result also because this one turned out to be 0. So don't care about that. And then for this one, it will be all 3. Okay, because the document 1 consists of 3 terms, right? So this is, so when we compute the cosine similarity, we get 0.6. Okay. So if we compare with the previous example with this, we are saying that the to be or not to be is closer to document 2 compared to do and document 1. Okay. Any question? Okay. So what are the advantages and disadvantages? Okay, for the advantages, there are 4. So the first one is it improve the retrieval quality because now you will be able to perform the ranking and also to do the partial matching. And the cosine similarity function assign a degree of similarity, allowing rank retrieval rather than binary results. So compared to Boolean model just gave you true or false, but the cosine similarity allow you to quantify the differences between the query and also the document that we have. And at the same time also we have embed the normalization in which you consider for long document you will be able to compare with a short document because you have normalized the weight of the component by dividing them with the length of the document. So up until now, this vector model is very popular. Even the LLM is using this as a basis So who introduced this one? Do you still remember? Shannon. Okay, so he's the one who introduced the vector model. So this is being applied now in many areas. Even now they use multimodal to describe image, text, and table at the same time to connect them to build a more intelligent decision system. So in next semester you will be taking machine learning, right? So in this semester you're taking this information retrieval, text mining. So we are dealing with unstructured data. Next semester you'll be taking machine learning, dealing with structured data or um, relational table. And then we will look into how do we complement these two to build a smart system, intelligent decision system. Okay, disadvantage of this vector model, as I mentioned, they assume term independence, which means that we cannot capture two terms or three terms that occur together. For example, computer science, ICT, network engineering. So we can do that one by constructing another table, but this time we have two terms um, we capture, not individual. Um, at the same time, also we have no semantic understanding um, how two terms are associated with each other, even if we can capture the number of time they exist together. So that one is going, I think, more into natural language processing. The um, word embedding. So the word embedding will tell you the meaning of the term, the context they are being used, and then how different they are from the other word. So this one you will learn in natural language processing, which is next semester or in year fourth year. Okay. Okay. Any question? If you're okay, can you type number 1 million? Why you don't put 1M only? Okay, can you type 1 zettabyte? 1 zettabyte. What is 1 zettabyte? Yeah, how many number of byte is 1 zettabyte? Which is 1 billion gigabyte. Okay, so find out what is 1 zettabyte. So that is the number of hard disk that you should have in the next 3 years. Okay. Any question? No question.